Hi guys, welcome to the next lecture in the course. And this week we're going to be looking at image processing and recognition. So I'll just start at the beginning and explain the details of this one. I can show the slideshow from the beginning here. So we're looking at, once we capture an image, what we can do in terms of image processing and then actually recognizing some patterns coming out of it from there. So let's say this is the first thing we do when we capture an image, as I might have mentioned before. Visual sense being a very important sense, of course, because we make sense of our environment by the images we get of it all the time. Humans, you can see the amount of data we gather with our eyes all the time. And of course, it's the same in theory with a computer vision system. We get a great deal of information in a single image. So this is just a very simple image. For historical reasons, it starts in the top left corner, counting along the columns and rows. Now, if you have just a grayscale image, which we've been working with in the tutorial, then we just have 256 gray levels. So each pixel has a number associated with it, which is a brightness, ranging from black 0 up to white 255. So you can imagine that as the number of pixels go up, the processing increases dramatically. Obviously, the processing increases with the square of the size of the array that you've got in your camera in terms of the pixel array. So, we don't need resolutions that are wildly higher than what you might need for any given application. So convolution is something I want to talk about. I might have mentioned before, but it's the way that the image processing is achieved is through convolution. So what this boils down to is where you have a mask which you apply to the image, and then you alter the central pixel in the mask in relation to the pattern of the pixels around it, as it's saying there. So this is what happens all the time when you use image processing software to do things like blur, sharpen, and edge detection as well. So you can see that this image has been blurred because it's applying probably a small mean filter where you just take an average of all the pixels over a small. So you have a mask and you move it across the image iteratively and you process the whole image using the mask. And that mask is called a kernel in convolution. And this is a simple kind of kernel here. The kernel will always have, it can be any size, but obviously the smaller it is, the less processing you've got. And it has to have an odd number of rows and columns because you have to have a central pixel, which is the one you're going to change. And the numbers in the kernel, as you can see you've got some numbers here, determine what it does, how it works, the effect it has. So you get different types of combinations for things like edge detection, for example, whether you're detecting edges in the horizontal or the vertical. You have different types of edge detector have different numbers in there. Now, convolution is a very important technique. It's used all the time. So those numbers I just mentioned are the numbers by which you multiply the actual value of the pixel in the image underneath it. And the number of that pixel is, of course, representing the intensity of the pixel over which a kernel element is hovering. The process multiplies each number in the kernel by the pixel intensity value directly, as it says. And so you get as many products as there are numbers in the kernel, of course, and this is how it operates. So you just multiply these numbers together, and then you're going to sum them all together. You get a number there. Okay, now the mean filter I just talked about a minute ago, which has a soft blurring effect. If you were applying the mean filter, then you'd actually then divide that total. You'd have ones in all these numbers here if it was a mean filter, and then the sum you would just divide by the number of elements in the kernel. But that's useful for getting rid of. One thing you can do with the mean filter is getting rid of noise, because you can imagine that it gets rid of the speckle noise quite effectively. But one disadvantage is that it tends to reduce the resolution of the image a little bit. I mean, one famous example of the mean filter was the images they sent down from the Apollo landings on the moon. They applied a mean filter to try to reduce the speckle noise in those, for example. There's many, many examples of that. It's a relatively simple thing to do, so it's quite convenient sometimes. As it says there, the final step of the process is to sum all the products together. And this is, I just mentioned, the case of the mean filter divided by the number of elements in the kernel. And that's a new intensity value for the pixel that was directly under the center of the kernel. So there we can see a little VI edge detection with 2D convolution. So you might want to have a play around with that VI. Probably allows you to change the type of filter, and then you will see the numbers changing in the kernel that's applied, and then you can see you apply, that's the original image. You apply the filter and you get the edge filters, you get the edges showing up nicely. This is quite handy sometimes because it gives a relatively standard way to measure the distance between two edges in an object to get the overall size of an object, which is quite handy sometimes. Because what you're trying to do in machine vision is that you're trying to reduce the data really a lot of the time. In traditional classical machine vision, you take an image, it's a grayscale image, there's loads and loads of information in it, the computer can't interpret. You well, not unless you use deep learning or something. You simplify it by thresholding it, so you just turn it into a monochrome image, black and white, which is less data, and then you apply an edge filter if you've got an object you're trying to measure in there, so all you're interested in is the edges, so that you can just get rid of everything else apart from the edges, you're reducing the data again, and then you can just measure that distance across there, across the top of the box, say. Now, thresholding is something you've probably already done, but now, it's not a brilliant image, I suppose, in terms of showing thresholding, because these two images look quite similar. But if you look carefully, you can see this is actually on the left a grayscale image, a typical snow scene. And then we've applied the filter, which you've done in LabVIEW, you've done in Vision Assistant. And anything below the threshold value is set to black, and anything above it is set to white. Actually, there's one little thing I could mention that might save you some trouble. It catches most people out, but it caught me out years ago. And that's that when you're in LabVIEW, okay, and you're doing a threshold, okay. As I say, when it does the threshold, it sets the white to 1 and then the black to 0, okay. Now, what you might find if you then try and display that image, the system might default to using a grayscale palette. A palette is a way that the program uses to display an image. It tells it how to display the image. If you have a color palette displaying a color image, grayscale is usually the default. So probably default to grayscale. Or you can have, but the point is that if you've got a binary image, you need a binary palette to display it. If you're inadvertently using a grayscale palette, which I remember doing years ago, getting confused with a black image coming up, that's because the grayscale palette interprets the 0 as black and the 1 as more or less black, if you know what I mean. But you need the binary palette, and you need to tell the VI that's displayed, WinDraw, you need to feed in a binary palette into it. This will all become straightforward when you do it with LabVIEW. Now, another thing you can do, of course, in terms of data reduction is erosion and dilation. Now, erosion, not surprisingly, erodes the contours of an object. And dilation has the reverse effect of erosion. It expands the contours of an object. Now, what they call a close operation is a dilation followed by an erosion. So there you add a load of pixels, a layer of pixels on, and then you take a layer of pixels off. Now you can do this as many times as you want. You can do multiple erosions and multiple dilations. And you can imagine that the close operation fills in tiny holes and smooths boundaries. Okay, so in LabVIEW, I think you might have been trying to use fill holes, which is a VI that comes with it, which fills in holes in objects, in particles. But you could do it manually by applying these close operation with the dilation and erosion, because that's what fill holes basically doing. Okay. Yeah, so opens the opposite of that really, where you have an erosion followed by dilation. You can imagine this, for example, if the thing gets bigger and you fill the hole in, then once you've done that, no matter how many times you erode it, you've lost that hole, haven't you? That's why close is very good at filling the holes in. Opens the opposite, where you remove something and then you make it larger. This is good for getting rid of very small objects. So we talked about getting rid of speckle noise in an image using a mean filter. Well, this is another way of doing it, these open operations, because if you've got very small particles, you do 1 or 2 erosions, you probably just get rid of the particle completely. And obviously, however many dilations you do, after that, the particle's gone, so you've lost it. So you got rid of noise, really, get rid of small objects. Yeah, so that's the idea of that. So this is showing the, you may be starting off with this particle, which is blue, the whole thing's blue to start with, and then you do a dilation on it and you get to green, which is a little bit like adding a layer of making it bigger is what dilation means, and adding a layer of pixels all around there. Then if you start with the blue and you do the erosion, you're just removing a layer of pixels and you're getting back to the yellow. So that's a nice little graphic showing what we're talking about there. Some morphological dilation and erosion. Skeletonization, again, there's a VI in LabVIEW for this. And not surprisingly, it's a process of reducing foreground regions in a bioimage to a skeletal remnant, they call it, that largely preserves the extent and connectivity of the original region. So you're trying to keep the structure of the original region, but with less data. And this way of visualizing this is that the original object has an external boundary. You can imagine being made of a slow burning material, and then you light it all around the boundary and it burns away. And the midpoints of this situation here is where they call the quench line. You can imagine if it's burning from both sides, the ash ends up in these little lines, perhaps, and that's the skeleton, as it's described by skeletonization. So that's worth knowing about. Quite useful for data reduction. Now, pattern recognition, you see, because there's two things you want to do in machine vision, really. You want to do the image processing, where you try to process the image to get it more suitable for what you want, more useful. You get rid of noise, maybe alter the distribution of brightness intensities, whatever you want to do to make it more useful. And then you're looking for certain patterns. The humans are pretty good at pattern recognition. For example, face recognition, that would be an example of pattern recognition. And computers can do it in various ways. We're talking about classic machine vision here, so we'll cover some of the basic ways it's been done in machine vision before now. Or feature detection could be another way of describing it. You're looking for specific things in the image that are of interest. And now the ways of doing it classically that have been considered are, of course, template matching, finding, matching, or counting specific patterns. Now, this is probably the most basic technique for doing it, the most essential one people think of. And I think there's even an example of doing it in the machine vision Vision Assistant tutorial, where you're looking for these brackets. But now, this is an object, obviously, that we're looking for in the image. So it can be a bit tricky because the object could be rotated. If you're just using a straightforward pattern template and you apply it and things are rotated, you won't see it. So you really want something that can work even when it's rotated, maybe partially hidden by an object or certainly varying in size as well. But it's a basic technique which is very useful in a lot of applications in industry. It's been used for many years and certainly worth being aware of. It's probably the first thing to think of if you've got a simple machine vision application and you're looking for some feature. Another one is polar signature. Now this one is where you find the centroid of the object, middle there, and you measure the distance to the edge of the object, and you plot that against the angle. So you've got a line here which is rotating around, and you're measuring this distance to this line, and then you're plotting it against the angle against the distance. Now, you could then use curve fitting or statistics to quantify the profile and get some information on this shape. And of course, one advantage of this has got is that it's resistant to the effects of rotation of the object. Because if I start rotating this object, this plot's going to be the same, it'll just be shifted along the x-axis. Okay, so it's pretty good in that way. There's that book by Alcock, Applied Image Processing, which is in the library, which goes through these traditional classical machine vision techniques. It's worth having a look if you get a chance. Now, this one, perimeter squared over 4 pi times the area, is the object irregularity. I mean, also called the Hayward circularity function in LabVIEW. But the important thing about this is, for a circle, the value is 1. So the least irregular shape you can get is a circular shape. And as the irregularity increases, this number will increase. And it's actually a very handy, simple way of measuring particle characteristics, really. I mean, I did various projects looking at the irregularity of the particles of the, in this case, water atomized iron. And as the irregularity increases, the density with which this stuff fills containers decreases. So that's quite important for many industrial processes. And also the flow characteristics of the powder will change depending on the irregularity. So if we can quantify irregularity, and I was doing that with a microscope and years ago, there's lots of ways of doing this, but you could use an electron microscope if you wanted to, but I was using an optical microscope and what they call a stereological method. So just basically like this, looking at cross-section images, really. Or just like, you could view it, you could think of it as being put on a lighting table and looking through it, but these things are only about 30 microns across, 40 microns across, pretty small particles. But anyway, you see the stereological means that you're taking 2D images and inferring something about the 3D characteristics of the shape, really. So with this, it's a nice simple measure. Okay, Prim square root of 0. It's something that can be measured quickly and easily. It's got this big advantage that it's the same value no matter if you rotate the object, of course, and then if you scale the object, you look at different sizes of particles to still be robust. You want to, if you're measuring irregularity, to have something which is not affected by orientation of the particles of the object or the apparent size of the object. So that's irregularity. And that could be, in some applications, you look at, and it's something that's used in the Vision Assistant tutorial, but they're looking for circular metal features on the metal and getting rid of ones that aren't particularly circular. And it's quite interesting in that way sometimes to do that. Now, another subject which I want to talk about in some depth is neural networks. And I'll spend a couple of lectures, 2 or 3 lectures talking about this because this is quite an important subject nowadays in machine vision. I don't think I could give a course on it, or computer vision, without talking about neural networks because they're used a great deal in machine vision, computer vision research. And this technique is inspired by the biological nervous system such as we got in the brain, really. And you can think of this, obviously we've got a large number of highly connected processing elements in the brain, so this is just a very simple sort of analogy, really, that where the computers work. The computers aren't built directly in this way, of course, nowadays. We're using a digital computer, which is a standard, conventional, traditional digital computer, but it's emulating this operation. It's simulating the way that the neural network works. Now, don't worry if you don't fully understand everything I'm talking about here, because I'll go over it again in some detail. It's quite an involved subject, as you can imagine, so you can't expect to get a full understanding immediately on this. It's an interesting subject, or a very relevant one, but a rather complex one, so we'll just take it a step at a time. But before going on about deep learning, and just as I mentioned before, deep learning has got a technique in it called convolutional neural networks, which we use a great deal. But before getting into that complexity, I just want to explain what a traditional, conventional neural network is. So it's basically a pattern recognition technique that learns through a learning process. And in biological systems, of course, the learning occurs through adjustments to the synaptic connections that exist between the neurons. So this is true of neural networks as well, but in this case, the training affects the weights associated with the links between the neurons. So this is a simple little neural network with 2 inputs and 2 outputs, and we've got a hidden layer with some neurons in here. Now, the weights I've just been talking about are simply multipliers that are associated with the links. So each link has a multiplier associated with it. So if a number is going in, it's multiplied the multiplier, and it goes into the neuron. Now, that's where the model resides in a neural network. That's where the model is, these combinations of weights. So they start off randomly assigned, and then during the training, they converge on certain values, which tends to let the neural network model whatever data you've got. It could be something simple, to start with. It could be just a curve rather than a straight line. It could be just a curve of data. And normally, if I'm in industry and I'm trying to model some data, I would probably start off trying to model it linearly. That's the thing that's typically done, just linear modeling of the data. But the trouble with that is that most processes in industry are not linear. Most are non-linear, in fact, highly non-linear most of the time. So just applying a straight line to modeling something is a bit of a crude and not very effective way of doing it. You can try applying curves to the data you've got to try to compensate for the non-linearity, and then you could use regression analysis after you apply the curve. The problem with that is that the nature of the curve is something which is not clear sometimes. I mean, it could be an exponential, it could be a quadratic. It's hard to say, especially when there's a bit of noise associated with the data. And especially, which quite often happens, where you've got a number of inputs, like you've got 2 inputs here and 2 outputs. So it's not just 1 input and 1 output, it's a bit more complicated than that. So determining trying to do regression on multiple inputs, giving you certain outputs, is a rather complicated process. And what you do is a process traditionally in statistics called multiple regression. Now, that's okay, but it's a bit complicated and it's hard to say what the relationships are. So nearly always people assume just a linear relationship between the inputs and the outputs. But of course it may not be linear. In the neural network, the great advantage of it is that you don't assume any kind of relationship. It's just that you've got these inputs, you've got these outputs, you train the model such that there's a good relationship between the two, and then that's your trained neural network. So, once a network's trained, you can consult it. In other words, you can put values in and see what comes out. And you can use that to help you get an understanding of certain industrial processes that you might be looking at, where you need some modeling. You can apply this to all sorts of, just about anything really, where you've got pattern recognition requirement. People tend to not use it that much in industry because they like to have equations, and there's no equation here. The model's in the network, and they find that a little bit like a black box, some people. So they get a bit worried that they don't understand the details of how it works. But it does work reliably and effectively and powerfully, so it should probably underutilized, I would say. Sorry, I'll just go back to that one again. The way this works is that each neuron has got a transfer function associated with it. Now, the transfer function is just a relationship between what value goes into the neuron and what value comes out. Okay, so the transfer function will actually be non-linear, and you probably in reality have more than one hidden layer. Okay, you just have another layer with all the neurons connected together. Because doing this enables you to measure, to model non-linearity. I mean, years ago, this neural network was actually developed by a guy called Rosenblatt, who was quite a sort of a Renaissance man. He was interested in contact with extraterrestrials, for example. He built an observation telescope on a hill behind his house, and things like that. So he was quite interested. He popularized the idea of neural networks quite a lot. In fact, he over-popularized them. He had an article in the New York Times talking about how he thought that neural networks were going to explore the universe, were going to reproduce, were going to be conscious. And this was all reported in the New York Times in 1958. And of course, it didn't happen. So a lot of people lost a bit of faith in this, so it went out of fashion a bit. And also, another reason it went out of fashion is that years ago, they just had one hidden layer, and they weren't able to model nonlinearity, which I just mentioned is pretty important. But people realized that with more layers, especially with nonlinear transfer functions, they could model nonlinearity. And suddenly, this was realized probably in the 1980s. And at the same time as that, another very powerful breakthrough occurred, okay, which is backpropagation. So the simplest type of neural network is something called feed-forward backpropagation. Okay. Now what that means is that it sounds complicated, but it's not that complicated. Okay, because you put some values in, they're fed forward through the multipliers, through the transfer functions, and you get a value out. That's what the feed-forward bit is. Okay. Now in the training, you get that value out, you compare it to the value you expected to get it coming out, and you get an error. Okay. Now that error you look at, and you go back through the network, modifying these weights, and that's a backpropagation bit. Okay, so you go back, modifying these weights, seeing what you can do to minimize this error. So that's why it's called feed-forward backpropagation. And this was invented a few years ago, in the 1980s. And maybe be Hinton who invented that. I'm trying to remember, but you can look this up. But anyway, Geoffrey Hinton might have invented that. He certainly did a lot of work on neural networks. And so with this feed-forward backpropagation, you can suddenly train the network. You can suddenly train it very easily, and you can train it to find a relationship between these inputs and the outputs for a whole range of data. Okay. But there's one thing I should mention before I lead the topic of this, really. I'm sorry to labour this, but it's quite an interesting subject, which I think you need to be aware of a little bit. And it will also give us a nice little lead into convolutional neural networks, which is such a hot topic, I mean, I went to a couple of conferences in recent years, and so many people are talking about advanced, generative adversarial neural networks. These are types of deep learning. Everybody's using deep learning. It's a very, very hot topic in AI. And particularly in machine vision, computer vision, it's extremely hot. So to have a course in computer vision that doesn't talk about deep learning, I think you guys would be missing out. So I do intend to talk about it in a bit of detail. And a way of getting into that interesting subject and powerful technique of deep learning is to talk about conventional neural networks. Sorry, I left what I was talking about. Well, what I was talking about there is training. Okay, so then you train the network. Now you've got to be careful when you're training the network. Okay, because if you're not careful, you're overtraining. And it might be the analogous situation is that you can imagine that in conventional statistics, I might have some fairly noisy data. Okay, and if I start applying, I don't know if any of you guys have got into curve fitting much, but you can fit curves of different orders through the data. Probably a quadratic is very useful for doing this, for example. When you go to higher order polynomials, you can get polynomials that will go through all of the data, go through all the points. But if you're not careful, you're modeling noise or error, okay? Because really that data is not really valid, it's just that there was noise in the data. So if I got some other data for the same application at a different time, I'd find those points in completely different places. So my highly trained, very high order polynomial would not give me good general performance. So what we say is it doesn't generalize well. Okay, and that's true of statistics and curve fitting. It's also true of neural networks. So if I got all the data that I had and I just trained it, just all the data I happened to have at a particular time, and I trained it heavily with that, then I get some more data the next day, I'd find it doesn't work very well. It doesn't correlate very well. So that's why we need to have a network that generalizes as well as possible. So the way to make it generalize is the principal way of doing it is to split the data into training data and test data. Okay, so I might use 3/4 of the data for training and 1/4 for test. And the important thing there is that the network never sees during training the test data. Okay, it only sees once it's been trained. Then you test it on the test data, and and this is a test of how well it generalizes. In other words, how well it works for data it hasn't seen before. This is extremely important in neural networks. That one of the main challenges in conventional neural networks is to get generalization. Okay. The other ways of making sure you don't overfit it, as you like, is to make sure it's to limit the amount of training you do, or maybe limit the number of neurons you've got. That's the way of doing it. So that's like a little bit of a crash introduction to neural networks, but you can ask me questions about that and I'll go into it again. I'll cover it again, really. It's a very powerful data-driven technique, which doesn't presume certain relationships between inputs and outputs, but just simply everything is data-driven and based on the data. So it's very powerful. Now, as I say here, because it's a simple analogy to the human brain, it's not surprising that it's good for solution of certain AI problems or artificial intelligence problems, of which we get a lot in image analysis and, of course, machine vision. And it's quite, as I was just mentioning a minute ago, it's quite good in the case where you've got, you've got highly nonlinear data and you've got quite a bit of noise. It's quite resistant to noise, actually, yeah. And you could use neural networks for all sorts of things. It doesn't have to be image processing. You could use them for landing a plane. You could use them for any kind of complicated task where you've got lots of things, inputs and outputs you need to relate together, but the model's a little bit unclear. There's lots of variations that can occur. As long as you've got enough data, then you can model the neural network. The chief problem in modeling neural networks is getting enough data, traditionally. And especially when you were talking about convolutional neural networks, which are more complicated and larger networks with more neurons, so require more training. So people traditionally have required to get a lot of data. They needed to get a lot of data from them. There is a way over that, which I will talk about in a future lecture. And if you look at those papers I put on there, the papers I presented at those conferences, one's looking at automated detection of weeds in grass. Okay, and that's quite a nice paper for going into these, giving an explanation for these techniques that really help you in the presence of very little data. So one of those is called transfer learning, and the other one's called data augmentation. Now these are not for simple neural networks, these are for convolutional neural networks, which I don't want to get ahead of myself, but transfer learning, just in a very brief summary, is a technique whereby you use a network which has already been trained previously on a previous set of data, and then but it's not fully trained. There's a bit of training required. So you take, say, 1 billion images off the internet and train it on all sorts of different things, and then you get a limited amount of data from, say, weeds in grass, and then you apply that to it and train it with that, and it works surprisingly well. You wouldn't think that would work, but the additional limited training gives you pretty good performance. Not quite as good as if I trained the whole thing from scratch with loads and loads of data from graphs, but pretty good. Probably better than any other techniques that you could use that are not deep learning techniques. The other thing, data augmentation, is where you just take a limited data set and you augment it by things like imaging, taking the images and rotating them, or scaling them, reflecting them. You wouldn't think that would work either, but it does. It gives you a bigger data set and improves the learning process. This will become clearer. I'll talk specifically about it a bit later on. Now, as I say, there are all sorts of things you can use neural networks for. A paper which I wrote on some years ago is using neural networks for calibration of images in machine vision. So something I might have talked about is barrel distortion, okay, which is quite a serious problem sometimes with shorter focal length lenses. As the focal length, the distance from the center of the lens to the image sensor, as that becomes smaller, the distortion in the image becomes greater. And also the field of view becomes bigger. It's like when you have a camera, you can get zoom, a zoom lens on your camera. Really, what you're doing is changing the focal length, and you're zooming in and zooming out. Of course, by the way, zooming, you want to use an optical zoom as much as you can, because if you start using a digital zoom, then you might lose resolution. But with the optical zoom, you're okay. But when you get that smaller focal length, you get anything below about 8 millimeters, you're going to get some noticeable barrel distortion. So this is the actual object shape we might be imaging. And with this shorter focal length, it ends up looking like a barrel. So the first thing to do is to avoid doing that if you can. As I say, the best thing you want to do in machine vision is to get the best quality images you can, rather than try to take an image of the problem and correct it. But having said that, sometimes you do need to have a wide field of view, and you are trying to image things, and you will get a certain amount of barrel distortion. So how can we correct this? Well, the amount of distortion you get is generally proportional to the distance from the center of the image to whatever point you're talking about. So you get more distortion, errors near the corner of the box here than you do here. And so one technique, and there is a VI in LabVIEW for doing this, which works pretty well actually, in my experience. I tried using it, which will just correct it. And there are other ones that people have published over the years, which will correct lens distortion depending on simply the distance from the center of the image to the point in question. But with this paper, I was thinking about, that's what you call an axisymmetric solution. You're kind of assuming that this distortion, the lens is perfect and perfectly axisymmetric. So any distortions will be the same, whatever angle you're looking at, position you're looking at here. But of course, that's not the case in machine vision. So you need some calibration which is related to the particular lens you're using. And the idea that I was coming up with is using a neural network to correct radial lens distortion or barrel distortion. And that worked pretty well. The neural network was pretty resilient. So we're looking here at the exact errors. And in this case, you find the difference between where you expect the point to be and where it actually is. And you start modeling that rather than the actual distance, because it's more sensitive to the distortion in the image. I'll put this paper onto Blackboard for you, so you'll have it there, and that will be useful, I think. I can put any other papers we've published over the years on there, which I think are particularly relevant to the course, really. And so that's a basic introduction to what we're talking about in terms of image processing and pattern recognition. Just to give you some background, I'm available to answer any questions you've got about that. You can always drop me an email, or we can have a chat about it during one of the sessions we have. But I think a lot of it, you'll find that material in standard books that I've managed to buy for the course. So these are standard techniques which are available in Image Processing Handbook and things like that, which are standard texts on image processing, and very, very common and well known. So you should be okay with this. As I say, got any specific questions, drop me a line. Keep going with the Vision Assistant and LabVIEW, specifically the LabVIEW, get into image processing with it. And with LabVIEW, what you can do is you can try, because of these things, I can stand here talking, and it's quite okay for getting across the basics. But when you start actually dragging in these VIs from LabVIEW and testing them on images of your own, and seeing what you can do with the VIs that are for specific morphological operations or specific pattern recognition. That was when things start making sense, I think. I mean, one thing you can do in LabVIEW, for example, is just get a load of data and you start fitting lines to it or fitting different shapes to it. And that's quite interesting. There's quite a lot. They spend a lot of money on developing a package like LabVIEW, and there's lots of functionality in those VIs. The iMac comes with all sorts of functionality. It's worth exploring that. Just take an image and put different VIs on there and put on context help and see what you can do. See what image processing you can do. See what effects you can get from it. It's really quite interesting and informative just to play around with it and see how varying different parameters affects the performance of these VIs. So definitely do that, and I think that will help also with the assignment. To get familiarity with relevant VIs is really the best thing to do. You can do that through Vision Assistant, just finding out basically what they do and varying the parameters, and then you can start doing more complicated work, of course, in LabVIEW. Okay, well, I hope that was helpful. I'll see you guys next week. Thanks very much.